Hello everyone, I am Chakri Cherukuri. I work in the quant research group at Bloomberg. So in today's talk, we'll see how we can build advanced data visualizations in Jupyter Notebooks. I will start with a brief overview of Jupyter Notebooks, and then we'll look at an overview of interactive widgets in Jupyter Notebooks. And then I'll show you some examples of advanced applications, dashboards, and visualizations in different areas like machine learning and finance. So Jupyter Notebooks are an excellent way to promote reproducible research by sharing documentation, code, and interactive plots. We can provide complete transparency into our research and models. And the notebooks can also be easily shared because notebooks are just JSON files, so they can be easily shared and they're very low weight. And new technologies like Jupyter Lab allow us to have a fully developed integrated environment, development environment, which is almost similar to RStudio or Spider. So let's look at some of the features we have in Jupyter Notebooks. We can do extensive documentation. For example, we have complete support for all the HTML tags and CSS styling. And notebooks also provide complete LaTeX support, so we can write equations to explain our models better. And we can also use shortcuts for like markdown shortcuts to improve our documentation. And Jupyter supports various kernel backends like Julia, Python, and R. So now you know why it's called Jupyter. And there is extensive support for plotting in Jupyter Notebooks. We can have Matplotlib and Seaborn to provide static plots. So they are rendered as static images in the output cells of the notebook. And since notebooks run in the browser, we also have JavaScript-enabled plotting libraries. There is bqplot, which was developed in our group at Bloomberg. It's open sourced on GitHub. You also have libraries like Plotly and Boca, which provide some interactive capabilities. And finally, we'll look at interactive widget libraries. These are not so popular, and that's the main focus of this talk. Using these interactive widgets, we can build rich applications and visualizations right in the notebook. So the two libraries I'll be using in today's examples are ipywidgets, which are core UI controls like text boxes, sliders, buttons, etc. And then bqplot, which is an interactive 2D plotting library, which was developed at Bloomberg. It's actually built on the same framework on which ipywidgets is built. So bqplot can be seamlessly integrated with ipywidgets to build rich interactive applications. And the nice thing about these libraries is that the attributes of widgets can be easily linked using Python callbacks. Let's now look at you guys can see this. So now I'll be showing you some examples live in the Jupyter Notebooks. So ipywidgets has extensive documentation. You can find it on Read the Docs. So you have the complete widget list with all the code and the documentation right here. And you can also look at this documentation to understand how to lay out these widgets using various layout classes. And one more important thing is widget events. As I was mentioning before, you need to understand how to link these widgets using callbacks and events. So the code is right here. And there's also a lot of documentation on building your own custom widgets by writing the Python class and the JavaScript modules. So you can go through this website to get a complete understanding of how these interactive widget libraries work. And bqplot, as I was mentioning before, is open sourced on GitHub. Oops. I think it's taking a while. Okay, so let's now look at a simple example where I'll explain you how these interactive widget libraries work at a high level. So for every interactive widget, there are two components. There is the Python object, which is the interface which the user sees and uses. And then there is the visual representation, which is mostly implemented in JavaScript. For example, here we have an integer slider, and which you can give the description and the value. And this is the visual representation here, which is implemented in JavaScript. One nice thing about this widget is that the JavaScript is totally hidden from the user. But that's what provides all the interactivity. And the user just deals with the Python attributes. And when the attributes are changed, some events are sent. And by capturing those events and registering callbacks, you can create the interactivity. So let me show you an example here. So here, I'm creating an integer slider. And this is the slider object. And I can render it directly. And you see the visual representation here. And it's also important to understand the bidirectional communication between the Python backend and the JavaScript frontend. For example, when I move the slider value, the Python attribute value gets updated. And when I change the Python value in the backend, for example, the frontend automatically updates. So that's what I mean by this bidirectional communication between the frontend and the backend. And this is totally seamless. And one of the nicest features of these interactive widgets is that you just deal with Python code. There is absolutely no JavaScript you have to know. It's all under the hood and it's hidden from the user. I think with that background, let's now look at some examples. Okay, so first I'll start with theoretical machine learning examples. The first example I have is k-means clustering. So I want to highlight some nice aspects of the Jupyter Notebook. For example, here I'm writing some documentation which explains how this algorithm works. So let me give you some brief background on k-means clustering. It's an unsupervised learning algorithm. It's used for grouping or clustering a cloud of points in a high-dimensional space. So what we do is, we first pick randomly k points, where k is the number of clusters you want to create. And then we alternate between two steps. So the first step is the assignment step, where we take each observation and assign it to the cluster based on its closest centroid. So for example, we take sample 1, and then we look at which of these k centroids is this point closest to. Let's say it's closest to the first centroid, so we assign it to cluster 1, right? Similarly, we assign clusters based on the proximity of the points to the centroids. And once we assign the clusters, we recompute or we update the centroids by taking the average of all the points. And once we update and create new centroids, we repeat the cycle. And again, we reassign the clusters and recompute the centroids. And we keep doing it iteratively till we converge when the assignments no longer change. So this is called Lloyd's algorithm. And it's a heuristic algorithm because this optimization problem is NP hard. And it's a greedy approach. So there's no guarantee that you'll reach the minimum. And let's now look at a nice visualization which helps us understand this algorithm. It's all implemented in NumPy here. The whole algorithm is implemented in NumPy. So I'm changing the centroids and assigning the clusters, everything here. So let me run this example. So here we have 3 sliders representing the first slider represents the number of points you want to choose. And k is the number of clusters. And the cluster centroid, by changing this, we can fix the distance between the clusters, whether they're very close to each other or very far away. So let me start the animation. And we can see that the algorithm is getting updated in real time. And the centroids are correctly identifying the clusters, right? So let me change the number of points to 300. And let's choose 5 clusters now. And as you can see, the algorithm is iteratively finding the correct clusters and updating the centroids. I can retry the algorithm by assigning randomly different clusters. Okay, so here we see a problem. The algorithm got stuck in the local minima because it's assigning these two as the same cluster, right? As I was mentioning before, this algorithm is heuristic and it got stuck in a local minima. So now we can try to retry this algorithm and it correctly fixes the problem, and now we get 5 different clusters, right? So again, this kind of interactive plots will really help us in understanding this kind of machine learning and mathematical models. And as I was mentioning before, this is a nice example of literate programming. We are providing the documentation of the algorithm, and we are writing all the code here, and then we have a nice interactive plot which helps us understand the model. By tweaking different parameter settings, we can fully understand the impact of those parameters on the model. And the next example I have is gradient descent. So gradient descent is the first order optimization problem, and gradient descent is the workhorse of all the optimization problems we see in deep learning. When you do the backpropagation, the weights are getting updated by doing gradient descent. So let me give you some intuition of how this gradient descent works. So let's say we have a multivariate function f, where x is a multivariate input, and let's say this function is differentiable at a point A. The idea here is the value of f decreases when we go in the negative direction of the gradient. So gradient is the first order derivative of the function with respect to all the inputs. So when we go in the negative direction, we are actually going downhill, and we'll soon find the minimum of the function. So the gradient descent algorithm works as follows. We first start with a starting point. We need to choose a starting point, x0, and then we choose the sequence x0, x1, x2 iteratively by using the following update step. Xn plus 1 is xn minus eta, which is the learning rate, times the gradient. And since we are going in the negative direction of gradient, we converge to the minimum of the function. And again, this whole algorithm is implemented in NumPy. And now we can look at a nice demonstration of this algorithm. So here I have a non-convex function. That means it has multiple local minima. And depending on the starting point, the goal is to reach here. But depending on where you start and depending on the learning rate, we can end up anywhere, right? So here I'm starting at 2.4, which is somewhere here. And the goal is, let's see what happens when I... So as you can see, sequentially it's going downhill, and it reaches the minimum. But that's not the global minimum, that's the local minimum, right? Let's see what happens when you increase the learning rate. And as you can see, the algorithm is totally not converging, but it's totally diverging, right? So let's now start at a different starting point and see what happens. We can quickly see that the algorithm converges to the global minimum. So it's very important to choose the correct starting point. And let's see what happens when I increase the learning rate. So we saw that it actually ended up at a different local minimum, even though we started at the correct point. So what's happening here is, because of a very high learning rate, the value of next step from here, instead of being here, it actually went all the way till here, right? And from here, the gradient is very large, and also it did a big step, and instead of coming somewhere here, it actually went all the way here, and it totally found a different local minimum. So again, these kind of interactive plots will really help us understand this kind of optimization algorithms and models. And these notebooks can be used as training material when you want to teach these data science and machine learning algorithms to students. The final example I have is Gaussian processes. So some brief intuition about these models. So we start with a multivariate Gaussian distribution. So if you have a multivariate vector x, and the Gaussian distribution is given by two parameters, mu and sigma, where mu is the condition, the expectation, and the sigma is the k by k covariance matrix. So we can think of covariance matrix as points which are close to each other will have higher covariance, right? And Gaussian process is a regression model where we are trying to do here is learn a Gaussian distribution over a set of functions, right? So we start with a prior assumption that the model, that the Gaussian regression is normally distributed with mean 0 and covariance k. And later, as we see the training samples, we do a Bayesian update and compute the posterior distribution. And since this is Gaussian distribution, we can compute the mean and covariance in closed form, and we can keep adjusting it, right? So here again, I implemented the whole algorithm in NumPy, and let me explain how it works. So let's say we have a set of test samples for which we don't know the value of y, right? We are trying to compute f of x, and we don't know the value of y. So the model starts with the assumption that it's all zeros, right? The y is all zeros. That's the mean of the distribution. And as we keep adding training samples, we recompute the distribution and the regression line changes. And since it's a distribution, I'm sampling 5 points, 5 samples from this distribution, and we see that they're all over the place, and we can look at the standard deviation bands, and they are in between these things, right? So now, let me add a sample here, where this is the x and this is the y. We know that for this x, that's the value of y, and that's why the distribution automatically moves to take that point into consideration, right? And if you look at the uncertainty, we see that along this point, it's not uncertain because we know for sure that the value of, for that value of x, this is the value of y. And now if we keep adding inputs, we see that the uncertainty is resolved, and as we keep adding points, the model learns the regression function better and better. For example, between this point and this point, we have a lot of uncertainty, therefore the confidence intervals are very high. And if we keep adding points here, we see that all the uncertainty is lost, and finally we are able to learn the function much better, right? So that's the intuition behind Gaussian process. And this is the regression line. As we see more and more points, the model is able to learn the regression function better and better. And these kind of visualizations are very helpful in trying to understand these complex models. So Gaussian processes are actually used in Bayesian optimization. I'll not go into details, but the goal here is we try to find the next value by maximizing this acquisition function. And Bayesian optimization has a lot of applications in hyperparameter tuning and deep learning. So that's why Gaussian processes are very important. Okay, so let's now go on to financial use cases. In finance, time series analysis is very important. In bqplot, we created a rich set of selector framework where you can select subset of time periods and do any statistical analysis. For example, here, I'm trying to do the performance of S&P 500 index. So here we have the time series of S&P 500 index, which is a very important equity index in US. And we can see that the time series starts from 95 all the way till 2019. And here we have the histogram of returns. And in finance, when we build models, we make some assumptions. So the standard assumption is that the returns are normally distributed. But empirically, we can clearly see that that's not the case. There are heavy tails on the left, right? So there are very abnormal negative returns. And that we can easily see from here. But one aspect of financial time series analysis or any time series analysis is that we want to perform this statistical analysis on a subset of time periods, right? We want to see how is my performance looking during the crisis or during the dot-com boom or something like that, right? So we have selectors in bqplot. So let me activate the selector by clicking on the plot. As you can see, the interval selector responds to mouse moves. When I move the mouse pointer up, I expand the interval. And when I move the mouse pointer down, I contract the interval, right? And I'm doing some statistical analysis by registering callbacks. So whenever I move the interval, the start and end points are updated. And by slicing into the data frame, I can easily do any statistical treatment. So in this case, I'm computing the total return, for example, from this period to this period. And accordingly, I'm also showing you the trend line. And notice that the color of the trend line changes. If the trend is negative, it becomes red. And when the trend is positive, it becomes green. And the color and the thickness of the line also changes based on the trend indicator, right? The higher the trend, the thicker the line. So let's look at some interesting time periods. So this is the financial crisis. We would have lost like 40% if we invested in the index. And what's remarkable is this last 9 years. So if you did nothing but just bought the index, you would have almost quadrupled your investment. You would have got almost like 4x the returns. So again, the selector frameworks are very helpful. You can do like advanced time series analysis, and you can slice into the data frame and pick periods where you want to do the analysis and look at the results in real time. But here, I'm just showing you the performance of S&P 500 index. But S&P 500 actually consists of 500 stocks, which are grouped into different sectors. So when you're making equity investments, you'd like to look at the performance of all these stocks. So that's the next example I'm going to show you here. Yeah. So here, what we are trying to do is understand the performance of all the S&P 500 constituents. There are 500 stocks in this index. They are grouped into different sectors, like technology sector, utilities, and healthcare, and so on. So the crux of this visualization is this tile map, which serves multiple purposes. The tile map can be used as a heat map, like we can encode it with some numerical values, and each cell color will change accordingly. And we can use tooltips, and we can also use it as a grouping widget. I'm grouping stocks here based on the sectors. So here we have the healthcare and industrials, IT, etc. And you can also click and select specific cells so that I can look at the performance of these stocks and how the stocks were performing for the last 8 years. And here I can color code by different numerical values. So currently I'm doing by market cap, and we see that the usual suspects like Amazon, Microsoft, and Google and Apple have very high market caps. We can also color code by, for example, let's say dividend yield, and we can easily identify sectors which pay good dividends. For example, healthcare and communication services, they don't pay much dividends. But if you look at energy and utilities, almost every company in that sector pays dividends. We can easily see that from this visualization. And we can also color code by volatility. Volatility is the risk in the stock, how much the stock moves on a daily basis. So the higher the volatility, the higher the risk. That's why I'm coding everything in red. And these stocks are extremely volatile. So if you click, you can see that the stock is going all over the place, right? And we can also color code by month-to-date return. So in the month of May, for example, the energy sector has not been doing well. We can easily see that from this visualization. And real estate has been doing well in the month of May, right? So let me click on specific stocks, for example, I'm going to pick tech stocks and see how they perform over the period of last 8 years. And equity curve is nothing but what is the value of $100 invested in this stock. So if I invest $100 in this stock, over a period of time, you see that the value almost like it went up a lot. And here in this table, I'm showing you different performance metrics, like what is the volatility, what is the Sharpe ratio, which is the risk-adjusted return, etc. And I can also compare with different stocks in the same sector or different sectors. Intel. So here, and then I can compare all these stocks by in the descending Sharpe ratio. So stocks having the highest Sharpe ratio are really good performers. For example, MA stands for, I think, MasterCard. It's a really good investment, as you can see from this. And you can also pick specific time periods to see the performance of these stocks, right? So this whole visualization is just built with bqplot and ipywidgets. As you can see, it's very easy to assemble all these widgets as Lego building blocks and make this rich visualization. And you can also search by names, for example, and see the values of this. It will automatically get picked, right? So that's all I have for this visualization. And as you can see, this it provides a very good picture of the overall US equity market in one nice visualization. And the last use case I have is based on a data set called Wealth of Nations. And here I'm going to show you like how to build these kind of visualizations, like what Tableau or other tools do. So let me explain this data set. Can you see it? Yeah. So here we have, I think, 200 countries, and we have 3 data points, and each of them is a time series. So for example, income, so we can start with 1800, and what is the value, all the way till 2008. So it's a time series here. And the life expectancy, and then we have population. And we also have the groupings of these countries based on the region into various groups. So this is a very canonical data set. And in tools like Tableau, we can easily visually select all these different attributes and create a bubble chart. And I'm going to show you in bqplot also we can do the same thing. So let me use a white theme here for a change. Yeah. So here I created a bubble chart. So the x-axis is the income, and the y-axis is the life expectancy, and the size of the bubble is the population, right? And as you can see, when you hover on each bubble, I can see the evolution of this bubble for different years, right? I'm showing this bubble for one particular year, 1800. All the values are for 1 year. And here I have the slider. If I move the slider, you can see the values of the bubble for different time periods. Like this is for the year 2008, right? And ipywidgets has a nice playback widget which I can click, and it will animate the whole bubble chart through time. So let me do that. And we can see the interesting evolution of these countries through time as we go forward every year. So all this playback button is doing is it's just linking to the value of the year slider. And when I update the value of the year slider, I go and update the bubble chart by linking them using callbacks. And here you see some interesting things. So obviously we have China and India and all the Asian countries, very high population. And you can see all the African countries here unfortunately, they have lower income and lower life expectancy. And we also see these small countries, Qatar, Luxembourg, Macau, Norway, and Singapore. So they're also like countries having very high life expectancy and income per capita. And you can see the color code based on the regions, right? So this is a very standard example, and I think there is a TED talk which is based on this. We just recreated that visualization in bqplot. And it's actually easy to build these kind of visualizations, and the code is all Python, so you don't have to learn any JavaScript or anything like that. So let's try to look at Choropleth. So Choropleth is the heat map, but it is rendered on a geographical map, so that we can look at the values, numerical values associated with countries as a heat map, but it is rendered on a world map. Yeah, so here we have the world map, and you can hover and look at the country, right? So let's pick one attribute for income, for example, income, and let's try to look at the changes over time. And now we can, instead of looking at the individual names, we can directly look at these changes on a world map. And one more nice thing about bqplot is that you can select countries, and you can register callbacks on the selected attribute. For example, here I want to look at the time series of China income from 1800 to 2008, and we clearly see that it was like after 1980s it just shot up like anything. And we can look at different countries and compare them. We can look at Brazil. So this aspect of bqplot is what separates it from other libraries. I can click on any chart and select specific components of the chart, and then by registering callbacks, I can update, for example, time series or any other plot, and that's how we can link different plots together. Now we can look at life expectancy. And also by looking at this visualization, we can see all the missing countries. For example, there's no data for Egypt and Russia in this data set. And we see that the life expectancy is unfortunately very low in Africa, but high in Europe, Americas, and Asia. For example, this is China, this is Australia, Norway, Indonesia, and Brazil, right? And we also can see that the availability of data points in this data set, right? So there is not much data available here. And finally, we'll look at population. So here we have the population heat map, and we clearly see that India, China, and Americas have the highest population. We can see that the US population increased gradually, but the population in India just shot up exponentially after the 1940s. And same thing with China, though it was gradual compared to India, right? So we can, so to summarize, in bqplot we can easily integrate and link different plots seamlessly, and it's all Python. There is absolutely no JavaScript. It's all hidden from the user, and bqplot is built using D3.js, which is a very popular JavaScript plotting library. And that's how we differentiate bqplot from other static visualization libraries like Tableau and other packages. I agree, in Tableau we can do everything without writing a single line of code by dragging and dropping. But in bqplot, we can do much more, and all in the Jupyter Notebook. And especially when you have to explain your models or explain your research, having these kind of interactive plots is extremely helpful in trying to convey your message to the stakeholders. And I think we have some time, so let me show you one last example. So let me explain briefly what this is about. This is called Twitter sentiment analysis. What we are trying to do here is, it's a machine learning problem. We are given tweets of companies, and we want to label them as negative, neutral, or positive based on the sentiment which is expressed in the tweet, right? For example, let's say if someone says this stock is a strong buy, that means it's a positive sentiment, right? So the label will be positive. Similarly, they say this stock is a sell, it's not doing well. That means the stock is a negative label. And the reason these sentiment labels are very important is because investors can build trading strategies based on the sentiment which is expressed in news and tweets. For example, they would like to buy stocks which have positive sentiment and simultaneously sell short or sell the stocks which have negative sentiment. So that's why what Bloomberg does is we provide this sentiment score as an enterprise data feed to all our hedge funds and other clients. And the problem with building these machine learning models on text data is that we need to first create the labeled data set, right? We need training data. So someone, unfortunately, needs to do this manually. So what we do is, and there is a company called Crowdflower and Amazon's Mechanical Turk. There are a lot of companies which manually tag all these tweets based on the sentiment which is expressed in the tweet. So Bloomberg outsources all these manual processes to consultants. And unfortunately, they don't have the financial expertise to tag these tweets. So they do make mistakes when they tag these tweets. And we get like, I think, around 100,000 tweets as a training data set. And then what we do is we split the data set into training data and test data set. And then we train the models on the training data set. And then using the test data set, we try to evaluate the performance of our models. And I built this dashboard to explain the performance of this model, of the machine learning classification model on the test data set. So what we do here is, on the test data set, we already know the labels, right? So by comparing the predicted labels with the actual labels, we can evaluate the performance of this model. And confusion matrix is a nice way of understanding the misclassifications. What it does is, it buckets the results into various cells based on the actual and the predicted labels. So by definition, all the diagonal entries are correct predictions because the actual label and the predicted labels match, right? And therefore, all the off-diagonal entries here, they are the misclassifications because the predicted and the actual labels do not match. So let me click on this here, this cell here, where the model is saying all these tweets are positive, but they're all tagged as negative by the human readers, right? So let me look at some example. Weight Watchers sees profit slimmed. So there is a subtle polarity inverting word, slimmed, which is totally changing the meaning of the tweet. And unfortunately, the model is not able to catch that. For example, here, this pie chart is showing the three predicted probabilities. And it's a logistic regression, so it's an interpretable model. So we can see why the model is making this prediction as positive, because it's giving a lot of importance to this token called profit. And the word slim is getting 0 importance. So it's a clear indication that we need to do some feature engineering to take into account these polarity inverting words. Let me explain what this is. We can visualize the model predicted probabilities, which is a tuple of 3 numbers, as a point inside an equilateral triangle. So the 3 vertices represent the 3 labels. And by looking at the points, let's say these points are very close to the positive vertex. So what this means is the model is assigning a very high positive probability for those points. And each point here represents a tweet here. And let's see how we can use this triangle to catch some data issues. So here I'm showing some, I'm selecting a cell where the model's predictions are all positive, but they're all tagged as neutral by the human readers. And if you think about it, that's where there is some subjectivity involved, right? So what makes a tweet positive versus neutral or negative versus neutral? The humans can get confused here. And let's see how the triangle visualization can help us catch these data issues. If you look at the triangle visualization, we see that the points which are close to the positive vertex are interesting because the model is assigning a very high positive probability that these tweets are positive. So let me use a lasso to select some of these tweets here. And these are filtered here, so let me read through these tweets for you. Microsoft sales beat street hopes. Cloud profits up. Allstate profit beats estimates. There's a price target raised to 49. There's a stock upgrade. As you can see, all these tweets are actually positive, and the model seems to be doing the right thing by making them positive. So these definitely look like data issues to me, and the way we found these data issues is by zeroing in on these points where the model is assigning a very high positive probability. So these kind of interactive visualizations and dashboards are extremely helpful in explaining complex models. We are able to fully understand how the model is making its predictions, and we also found how to fix data issues and identify data issues using this visualization. So I think that's all I have today. I want to thank you all for attending my talk, and if you have any questions, I'm happy to take them.
This is amazing. This is like very beautiful visualizations and also very interactive. I was wondering about the scalability of this visualization. Do you have any experience of what are the limits in terms of data size that you can safely plot and still be reasonably interactive with this kind of library?
It's an excellent question. So bqplot is implemented using D3.js, which is based on SVG. So what SVG does is, it creates a DOM node for each and every, for example, each scatter point, there is one DOM node. So if you want to plot like a million points in a scatter plot, it's not going to work well because it's going to create million DOM nodes inside the browser. And we are looking at canvas-based solutions for those kind of problems. But I mean, most of the time, it works really well. The interactivity is seamless. Only in those extreme cases where you want to visualize like millions of points, which are very rare, it will break.
And we can always downsample, right? At some point,
Yep.
if we need to. Okay, thank you very much.
Sure.